Okay, what's up? Welcome back to the channel. This is the Prokon Geek, and in today's video we're now moving on to the design of our beams. Okay, so if this is your first time coming to my channel, please just go to it and go to the subscribe button and click on it and subscribe to my channel. I cannot subscribe to my own channel, but you can, so please subscribe to the channel. And as you're watching the video that I'm about to give to you, please leave a like and also a comment in the comment box below so that more people are able to see these videos and benefit just as you. Alright, like I told you in the introduction, today we're looking at the beams, and obviously most of you are thinking, okay, this is how we design beams in Prokon. Yes, this is how we're going to be designing beams in Prokon, and we're going to design all of our beams in Prokon. But first of all, the thing is, you see this tab called loads is a very important tab because this is what defines whether you have done a good analysis or a good design. So I know it is the fifth tab. This is the fifth thing that we need to worry about. Actually, the last thing that we need to worry about before we actually analyze and design our beams. But it is very important for us to understand how we get to input these loads, because that is the difference between someone who knows how to use Prokon and someone who does not know how to use Prokon. So I was thinking the best thing is we start off with AutoCAD, and we also see what we call the beam distribution load theory back in AutoCAD, so that when we get to Prokon, you have an idea of what we are actually doing and what we need to do so that our designs are perfect, they're good, and they are on point. So to do that, what we have to do is just go back to AutoCAD. And yes, as we're defining our beams, we need to remember which beams are we talking about. We are talking about the first floor beams that we did when we were doing our first floor layout. So in this case, we have beam. The first beam that you have at the top is beam 1, then you have beam 2, and then you have beam 3. All of them are going to be continuous. They're not going to be single span beams, so we're going to design them as continuous beams. This is what I mean by continuous beams. I hope you already know what a continuous beam is. There is the best representation of what a continuous beam is. So we're going to design our beams as continuous beams, not single span beams. Let's just see what a single span beam is in case you do not know what a single span beam is. There is your single span beam. We're not designing it as single span beams, we're designing them as continuous beams. So to go back, we're going to go back to Prokon. So we have the continuous beam 1, continuous beam 2, and continuous beam 3, and then we also have continuous beam 4, which is the same and a mirror version of this one, so I call it continuous beam 4. And then we have continuous beam 5, which is a mirror version of this one as well, so it's continuous beam 5. And then we have continuous beam 6, which is independent and is on its own. The reason now, once you have your layout, the next thing that you need to do is come up with what we call beam distribution shells. As you can see, I've already done this distribution shells. This is for first floor beam number 2. This is the distribution shell, and then this is for distribution for beam 1. This is for beam 3. This is for beam 4. This is for beam 5, and this is for beam 6. So to understand the theory that I was talking about, we need to go to where these things work, or how you are supposed to get your loads when they're coming in, and also what these beams will be looking like. So this is exactly what we now need to talk about under notation. So let's begin our theory lesson. So to begin off, we need to understand how the loads from the slabs or the walls come to the beams, or we need to understand where do loads from beams come from. So loads that go to the beams come from 4 main things: from your slabs, that is whether they're monolithic, or from above, or the slabs are above in the case of precast slabs, or they can come from the walls that are above the beam, whether you have load bearing walls. Partitions, we don't really count them in, but you could still add them. Then you could also have beams resting on your beams. So these beams will be carrying their loads, transmitting it to the beams. For example, girder beams are beams which carry other beams. So their loads come from other beams. They can be point loads or distributed loads. Then the next thing is gantries. You also have gantry cranes or everything. Those also have their support provided by the beams, so their loads will be going to the beams. So that's the thing. We need to understand where the loads on beams come from. I've highlighted where they come from mostly. Now we need to see what happens. In the simple case, the most important thing we need to understand are the loads from the slabs. Because, for example, in our building, we only have the slabs and the walls providing their loads to our beams. We don't have beams providing loads to other beams, and we also do not have any gantries. So we have slabs and the walls. For the walls, it's simple. There is a representation. Obviously, your wall is going to be on top of the beam. All you have to do is to see the load, the line load, how many kilonewtons per meter the wall will be distributed to your beam as you flow throughout. Now, we need to look at slabs. So in the case of slabs, there are two conditions. You could ever have a one-way spanning slab, as you can see right now. This nice slab that you have on the screen, that is rectangular and has only beams, beam A and beam B. Then you have another option where you have beam C, beam A, beam D, and beam B. This is a two-way spanning slab, so it's a bit exaggerated. It is a one-way spanning slab if you really maybe look at the spans, but we just exaggerated it so that you get a clear view of what we're going to be talking about as we explain this theory. So what happens is, obviously, you're going to have a load that is going to be on your slab. It's going to be an area load, and then you're also going to have an area load on your slab as well. So what happens is, if it is a two-way spanning slab, this portion that I've shaded orange transmits all of its loads to the beam, that is beam A, and the portion that I have shaded cyan transmits all of its loads to beam B. So if it is a two-way slab, all you have to do is just break up the slab in two, as you can see by the gray line, and then the other half transmits its loads to the top beam, and the other half transmits its loads to the bottom beam, in this case B. So what would happen now? How do you find that load? This is how you would represent it. And W max is obviously the maximum load, the value of the maximum load. This is going to be a distributed load. This is how. So this is in plan. In plan, it will look like this. And now when you're analyzing the beam as a simply supported beam with these triangles representing the supports, this, let me just shade it for you so that you get an idea and you understand. So we're just going to pick an internal part. Okay, that is wrong. Let me just, this is what I'll do. I'll create a rectangle. Just go to there, and then I'll go to there. Then what I'll do is, I'll just make sure that it's solid. Let's make sure it is solid so that you have an idea of what we're trying to do. Then the next thing that you're going to do is pick an internal point to highlight so that I represent this shape load. The next thing is, let's do this. Let's make sure it is that. And then we shade 50. And then we make the angle 45. Okay, 45 is too much. So what we're going to do is put it at 90. Let's see, and at 90 doesn't work. Now at 45. So as you can see, these orange lines would represent the entire load that is being transmitted to the beam. It's a uniformly distributed load. And if you remember from your loads, you obviously have the maximum value of the load that is going to the beams. So that maximum value called W max is equal to W multiplied by Lx over 2, where W is the slab load in kilonewtons per square meter and Lx is the shorter span. So all you have to do is find, okay, what is the load that is going to the slabs? In our case, let's say it's 5 kilonewtons per square meter. That is the imposed load, or the total load. That is the imposed and live load that is going onto the slab. Let's say it's 8 kilonewtons per square meter. So all you have to do is say W, in this case, is, you see, it's 8, and then Lx is the shorter span, and in our case this is Lx. So for example, let's just see what this is. Let's see what it is. So that is 5430. So what you would do is you would say 8 multiplied by 4530 divided by 2, and you can actually, let's just put that in meters. So what you would do, let me use a Mathcad. So let's just say new sheet. So what it would transmit to, it would actually begin, let's just say W, the maximum load, would actually begin now, would be equal to, let me just define it. That would say W is going to be defined by, in our case, let's say the load is 8, then you would multiply that by 5 point, what is the value again? 430. 430, then divide that by 2, like this, and there you would get your value. And in our case, W would be equal to 21.72. That would be the maximum value, and that would be W in kilonewtons per meter. You understand? So what you would do, because obviously this is what it would be, you would say kilonewtons per square meter. So just put it per square meter, right, multiplied by, that would be meters, and there you would go. W would be, let me just show you that it is equal to kilonewtons per meter, and if it, that is what would happen. So all you would say is 8 kilonewtons per square meter multiplied by, let's just put some space there so that you guys can see clearly, 8 kilonewtons per square meter multiplied by 5.430 meters divided by 2. So the load, that is the maximum value of W max, in our case would be 21.72. That would be the load going to your beams. This is how you would distribute it if it was a one-way slab. Now we need to talk about the two-way slab. Okay, now that we have talked about the one-way spanning slab, the next thing we need to talk about is a two-way spanning slab. So in a two-way spanning slab, obviously your slab is going to be supported at all the 4 edges, and you're going to have 4 beams at all these edges: beam A, beam B, beam C, and beam D. So you'll see that the portion that goes to beam C is provided by this triangular section that I have highlighted in orange, and beam B and also beam A, because they're similar, will have their loads being distributed from this portion that I've highlighted, which is in cyan. So how do those loads now represent them? They are in elevation. So in elevation for beam C, this is how beam C would look like. So its length, the span of beam C, would obviously be equal to Lx, and then obviously the load on it will be W max, and also the load here for beam B, the span will be equal to Ly, because that is the longer side, and then the load, the maximum value for the load, will be equal to W max, which is now given by these formulas. So those of you who are failing to understand what W max is, what I'm just referring to is you need to know about the common types of loads which are on beams. So this is learnaboutstructures.com. So as you know, we have point loads, right? Then we have uniformly distributed loads, which is what we saw when we were looking at the one-way spanning slab. And then going back, we have the triangular distributed load and the trapezoidal distributed load. So these are the two types of loads now that come when you are having a two-way spanning slab: the triangular distributed load and the trapezoidally distributed load. So when you come down now, so the most important thing, obviously, you want to find what, for you to come up with your moment and shear force diagrams, or to come up with the moments and shear which is happening in your beam, because that is what beam design is all about. You need to find the shear and the moment, then reinforce your beam for that shear and the moment that is going to your beams. So now what happens is W max, in our case, it is given by this formula, which you can see, and where W is equal to slab and Lx is always the shorter side. And then for the trapezoidal load, okay, see Mathcad file, I'm feeling a little bit lazy now. So let me just pull up my Mathcad sheet so that you understand this formula. So for trapezoidal loads, slab distribution to trapezoidal loads, this is what happens. The formula is given by, you have WD, which is obviously yo. Let me just zoom in. Can I zoom in this? Yes, I can. Let me just zoom it in. WD is given by QD, where QD is the load from your slabs, the area load, whether it's 8 kilonewtons per square meter or whatever it is, multiplied by the shorter span divided by 3. Then you multiply all of that result by 1, subtract 1 over 3, multiplied by K squared, where K squared is called the span coefficient and is given by Ly over Lxa, where short span from the drawing is, so the short span from your slab. So I'm going to show you how you actually use this sheet when we actually now punch in the values in Prokon, so that you get an understanding of them. But I just wanted to show you the formula in a much better way as well, so that you understand what is the formula. It's equal to WD QD multiplied by Lx divided by 3 multiplied by 1, subtract 1 over 3k squared. Now for triangular loads, it is quite simple. It's just the slab load multiplied by the shorter span divided by 3. which is WDQD multiplied by LX over 3. If you go back to AutoCAD, that is what I was trying to represent with this little formula. So it's good to always know this formula so that you're able to calculate W max. So that is the most important thing. We need to find out what W max is. So whenever you have your structure or your shell, in this case with our layout, so what we had to do is we had to come up with a shell, and then you had to construct these lines now. So some people will be asking me, how do you construct these lines that show you that the area is the one that is given by the shade, which is in orange? So it is easy. When you have a simple slab like this, the theory just says all you have to do is create, let me show you another line, 45-degree line, then a 45-degree line. This is from the shorter side. This is what you do. Just create a 45-degree line, enter. All right, let me just repeat that. Let me go chop, and then enter. And there we go. So as you can see, all these lines are 45-degree lines. This is how you create the tributary areas so that you have an idea of the representation of how you represent them, or you put these loads to your beams. So this is it. This is the gist of the theory. You need to understand where the loads to your beams are coming from. So after you are done taking care of obviously the loads from your beams, from your slabs to your beams, you need to take care of the loads from your walls, and that is what we're going to talk about. How do you know the value of the load that is coming from your wall? Okay, so to get the load that is coming to your beams from the walls, in case you have walls on top of your beams, or just you have walls around your structure. In this case, we're going to have walls when we come. Let me just go to the first floor layout. Obviously, we're going to have walls on top because our building is extending, as you can see, is extending to the second floor. All our walls are going to the second floor. So now, if you have walls over your beams, the next thing that you want to do, this is Mathcad again. All you have to do is it's a simple calculation. Provide the thickness of the wall. You need to know the thickness of the wall. In our case, it is 230, but you can actually even put it as 115. You put it as 115, and then provide the height of the wall. In our case, it was what is it? It was 3 meters, but you can change it as well. If you want maybe a 4-meter walls, as you can see, it automatically calculates there. Then obviously you need, the next thing that you need is the unit weight of your wall. In this case, it's 23 kilonewtons per cubic meter if you're using brick that has a motor. Now to get the load, which is Q, it is simple. Gamma multiplied by H multiplied by T gives you, in this case, 10.58. You can change that as well. Let me show you the cool thing about Mathcad. So moment we change it to 230, we just change the load as well. Let's change it back to 3 meters. The moment we just change that, we change it back to 15.87. So Mathcad is a cool way that can help you to follow through your calculations and just have them presented in a nice way. So it's similar to Excel, but it's different from Excel that this gives you a user interface that is similar to how you would be doing it when you're doing hand calculations. So I prefer this when I'm doing my calculations that are a little bit monotonous and also have too much words that I need to provide, as opposed to the Excel sheets. So, and also if I have too many formulas that I need to know where this thing is coming from, or the theory behind the calculation of the thing, because Excel does not give you anywhere to put these formulas. You have to reference them as sheets. It would say this multiplied by this, multiplied by this, multiplied by this, and it's not just cool. So this is why I use Mathcad. So this is how you would come up with the load for your beams. So now I think that is it. You now have an understanding of how these loads are distributed to your beams. And now we can actually get into the design and configuration of our beams now, in taking it from Prokon, then going all the way, and taking it from AutoCAD, and then go all the way to Prokon. So what I'm going to do is, I just want this video to focus mostly on the beam distribution. Let's now move on to the design and the analysis and design of our beams in the very next video. So please tune into this series. Don't skip. It's your turn. Just go to the next video, watch it as we continue. The first thing that we're going to do in that video is design a first floor beam. I think the best beam to design, I think we should start with beam 1. It's an L beam, and then we move on to beam 2. It's a T beam. We would have done all the beams, and we can see if we can finish all of them, but let's do the L beam first. So please, if this is your first time coming to my channel, please hit the subscribe button And if you're coming to this channel and it's like your 50th time still and you haven't subscribed, click the subscribe button. Remember to like the video, leave a comment down in the comment box below. If you haven't truly understood this and you want me to go through it without rushing, or you want me to do another example so that you grasp it, please leave a comment in the comment box below so that I know. And yes, thank you very much for tuning in. Until next time and until the next video. Actually, let's just get into the next video. So drop this video, click the link, subscribe, like it. Let's get into the next video, ladies and gentlemen.